Okay, so today is a joint sort of project. It's the task 3 for the what not to do series, and it's also the intro part 4. Um, and it's because it combines. I mean, it is the task from the QOSF, but it's also the a good introduction since we just discussed multi-qubit operations. So in order to create a circuit simulator from scratch, the way I did this, at least, there's a lot of different techniques when it comes to circuit simulations. There's density matrix simulators, there's all this stuff, but this is simply just the sort of most intuitive way, I guess, to do it from what we've seen, and that is the state vector simulator. So that's actually a backend, I'm pretty sure, in like Qiskit and stuff, is you can have like different types of simulators, and state vector is a common one because it has advantages and disadvantages, and the advantage and simultaneous disadvantage is that you have knowledge of the complete state vector at all points of the simulation. Now, it's an advantage because that's a lot of information that you might be able to work with. It's a disadvantage in that it's not reflective of reality. We don't know that. And two, that can be huge to compute as it grows exponentially with qubits. And so that's not always great, right? If you want to simulate large qubits, that's not always the best way to go. So we can see the general setup here. We get our initial position, we do the operations, and then we get our measurements, right? This is the general circuit simulator. And so this is going to be user-defined input. This is what varies every time. And then there's some options here and some options here, but this is the bulk of the input. And so we're just going to specify the first thing to do is to define some gates. And so we need to define our gate set that the circuit simulator works with. And so, it's not, you could do like C naught, and you could do arbitrary unitary, and I'm pretty sure that's probably complete. You could represent any circuit with that, but that's not very helpful, right? That's not what most simulators have. So first thing you'll notice at the top is this is all built on NumPy for fast operations, and uses Python math. So the top ones are just common definitions. So the outer product, let me actually go back, is used a lot in these calculations. So if we have, so remember, inner product is this. This is inner product. Outer product is this. So inner product, right, is a number. It's a scalar. But this outer product is, so if this is a n column vector, this is a n column vector, this is a n by n matrix. So 0, 0 is 1, 0, 0, 0, and 1, 1 is 0, 0, 0, 1. Those are the outer products of them, and you can see that's pretty easy to do, right? 0, this is 1, 0, this is 0, 1. Oh, that's not 1, 0. So we do row times column, row times column. And we can see, okay, 1, 1, 1. I just erased that because that wasn't very clear. The outer product is actually, you'll more common see some notation like tensor product. You'll see that notation a lot. And so yeah, we can those are just common definitions that we use, so don't worry too much about them. We'll get into them in a second. But first we have to define the gate set. So we have the why does it highlighting keeps getting weird? I don't know why. So we have the polygates, X, Y, and Z. So notice this probably would have been smart to just make one type of gate, a master gate class that all of them inherit from or something, but that doesn't matter. So we have the polygates, so there's X, and notice they're defined by their matrix and their what qubit they're operating on. The way I have it set up is the qubits are ordered 0 to n, where 0 is the topmost qubit. So we have X, Y, and that's J is how you do imaginary numbers in NumPy, and Z. And then we have some more standard gates like H, the identity gate, the S gate, and then here's the arbitrary unitary, where you put in the 3 parameters, and you can get the gate here, and then so these are all just the single qubit gates. It's not a huge gate set. You could have T gates and other phase gates and stuff, but we just have the polygates H, S, and then you can make any gate, single qubit gate you want from that. Excuse me, but now we have the controlled object. So this takes a gate. This is sort of saying, okay, if you want, so the way I set this up too, just a heads up, you can theoretically, right, in like circ, you can do X, like circ.x on qubit 0 dot controlled by, and do arbitrarily many controlled by. This is set up so it will only work with, you can only have one control, and you can only control one single qubit gate. You can't do a controlled C0 or something like that. And so, yeah, that's basically how this works. This is a controlled class for any single qubit gates with single controllers. And then there's also the Rx, Ry, and Rz gates down here, where they just have a additional, param term in them. And so this is just a standard gate set. We've discussed X, Y, Z gates, H gates before. S is new, but I don't even use it, so it doesn't really matter. And then the controlled operation, right? In the last video, we discussed controlled NOT, the C0 gate, but you can also do controlled Y, right? The same principle is true. It's just if that top one in that direction is 1, then you can do the operation. That's all that controlled means. And so the first thing we want to do now, when we get into this, we want to import all the gates. We want to import NumPy. We want to import math. And default dict is just for handy. It helps with the formatting. So first thing we do is we can look at the format down here. So I have a bunch of example circuits. These are all examples of the circuit. So we can see the general format, right? We define the qubits, we define the circuit, we run the circuit, and we print the results. Oopsies. So that's how I format it. So we can do more complex things. For example, here's the Bell state we talked about last time, Hadamard and controlled X. And so you can see in this, excuse me, in this simulator, we have this state vector that's defined with the initial qubit. So first we define a number of qubits we want. I've only tested this like up to 10. Once it gets to 15, it gets really slow, so it's not very efficient, but it works. Also, I'll talk about problems and its efficiency in a second. But yeah, so basically, right, we set it all to zeros, right? We have a 2 to the n number of states for n qubits, and we set the starting state, right? This is going to be a column vector. We set the initial starting state to be the ground state, which is, the very first position is 1, because the state is all zeros. That's the only state that exists. And so then, now that we have the state vector, we can think about what do we have to do. And so this is where we have the general circuit framework, right? So we run the circuit, we have the input qubits, we have the circuit, and we have how many measurements we want to take. So what we need to do is we need to basically go through the circuit, do all of those operations, and then measure it. That's pretty much the simple, right? That's how the circuit was set up. So first we'll talk about the measurement, the last part, because that's easier. So we have the qubits, the final state vector, right? All the operations have been done to the qubits. And so what do we do? Well, the first thing we do is for formatting, right? It was a n by 1 array, just so you could do matrix multiplication, but we really just want a length n array. And so then we excuse me, we can get the probabilities of measurement by squaring this, or really multiplying it by its conjugate. And so the reason you do this, remember, is because the amplitudes are not actually the probabilities, they're the probability amplitudes, which means you square them to get the probabilities of measurements. So we have to square it, which is what we do here. We multiply by the conjugate to get the measurements. And then this will give us, right, the probabilities for each state of measurement. And so this is what we do, right? We collect the measurements by choosing randomly from the number of states. We measure this, 1,000 times, and the probability distribution is defined by the square of this measurement. We create a default dictionary to return. This is just so that if I call, for example, if I want to see how many zero, or if I want to see a specific bit string that was returned, but there was no like terms in it, right? Then it'll just return 0. And so that's just for convenience, right? The default value is 0. It's not measured ever. And so that's just for convenience. And then we want to, excuse me. What we want to do is we want to convert each number into the binary value that we have. And so this is just a technique. So we say, so we have this n is the number of possible states, which is the length of the bit string. Basically, the length of this bit string is what this represents, because we're doing the log base 2 of the qubits. So this is basically maybe the easier way to explain this is just getting the number of qubits, which is also the length of the bit string. Obviously, it's the same as the number of the qubits. Then we convert the measurement for each measurement we made. It's going to give us a bit string. We convert this bit string, oh, that's handy, into a binary number, or a binary string rather, just because strings are nice and pretty. And then we fill it to be a certain, so every string, right, even if we measured like 0.00001, that would just convert into 1 in binary, but we want all the zeros because that's the actual bit string. And so then we increment that value for how many times it's been measured, and we return the total number of measurements. So that's pretty straightforward. We can then see that the challenge now is, okay, well, how do we get this final state vector? Well, we can look through and we can see here is so for each part of the circuit, for each operation, we need to convert it into a matrix of size, of the qubit state vector size, and then we can just multiply it, right? We can just apply it to the gates to the qubits. And this, remember, is the handy way of doing matrix multiplication. I like using it whenever I can because it's a fun symbol, I think. And so so this has to be a vector, or a matrix that can be multiplied. And so this has to be 2 to the n by 2 to the n values, right? Because the state vector is length 2 to the n. So, well, it's 2 to the n by 1, right? So we need a 2 to the n by 2 to the n matrix here, which will then yield, right? So if we do 2 to the n, 2 to the n, we do this times 2 to the n, 1, this will yield us a 2 to the n, 1. And so this is what we want, right? This is the formatting we want. So now how do we convert, for example? Let's suppose we have 10 qubits and we want to apply the x gate, right? The x gate's just one qubit operation, so it's 2 by 2. How do we convert that into this huge, 1024 by 1024 matrix? And the key here is what's going to be the biggest part of this code, right? Which is the get op operation. So we take the qubits, which is really, I should really not call this qubits because it's really the state vector, but yeah, potato. And we get the gate. And so Q is the which qubit, the integer value of which number qubit it's acting on, the gate is supposed to be acting on. This is the number of qubits, so the log base 2 of the state vector. So the first thing we do, which I'm not going to talk about now, is we see if the gate is a 2 qubit gate. So we see if it has the attribute 2 qubit, which it does not for the single qubit example. So we'll skip that for now. I'll talk about that after this. So the first thing we can do is, okay, if there's only 1 qubit, we don't need to do anything, right? We're doing a single qubit operation on a single qubit, bingo, done. However, if it's not the case, then what we need to do is get the ops for every single other qubit, right? Because when we step through this, when we do one step of the circuit, but the step is only operating on 1 qubit, every other qubit has no operation, which means every other qubit has the identity operation. So what do? So we collect all of these values. So this is the we get the we iterate through all the number of qubits. Remember, this is n values. And so we can say, okay, well, if this is the qubit we're acting on, append the gate operation. If this isn't the qubit we're acting on, then just append the identity operation. And then we're going to create the big old matrix. So what do? We do the Kronecker product. So this takes the gates, and this is like the tensor product we've seen before. And so if it's 2, if this is a 2 by 2 matrix and this is a 2 by 2 matrix, this will result in a 4 by 4 matrix. And then we can keep doing this. So this is sort of what we do, right? We add we combine them together. This is a lot of work to do by hand. But for example, I'll do a quick example of a 2 by 2 matrix, right? So suppose we had this is an example that isn't realistic. I'll tell you in a second why, but suppose we had so we have X, right? What matrix is this, right? Well, we know X is H, is 1, 1, 1, negative 1, all times 1 over square root 2, but I don't care about that. So what this results in is that is not right. So this is 2. This is a 2 by 2 matrix. Each one of these values now becomes a 2 by 2 matrix. So this becomes 0 H H 0, or this becomes it's going to be a lot to write out. 0 0 0 1 1 1 negative 1 1 1 1 negative 1 0 0 0 0. Right. This is the operation being done. However, the reason I say this is unrealistic, I mean, this is perfectly possible, but in our circuit, and this is also where the, oh God, oopsies, my bad. This is also where the inefficiency comes in. I only process one operation at a time. So if I go back here, right, in my circuit, this would have to be 0 0 X, I, H, right? And so then you're really, these can be done at one time simultaneously. However, I don't implement that in my circuit, which significantly slows things down, right? If you do a Hadamard gate on, your 15 qubits, you actually have to do 15 different operations rather than combining them into one. And 15 matrix multiplications, at the size, when the matrix is 2 to the 15th by 2 to the 15th is really expensive. So, if you're looking for, I guess a lot of what I've done so far is just telling you how to do things. But if you're looking for an example and you want to try something and, implement it, then you can look how to do this, and you can actually implement synchronous gate applications. So if I look in my code, and we see over here, right here, right? This could be combined, if you have down here, if you sense, so you would probably do something right here, right? You'd be like, if ops are compatible, then you could combine them. And then in here, you could just replace this, right? Like if I equals Q, or if I equals the whichever other op it's being acted on, then you could set that equal to it, and you could just do the same Kronecker product. But that's a little bit challenging. But if anyone wants to do it, you can actually, when you do actually do it, you can submit a pull request to the repo, and that would be fine. And so, yeah, so that's the basic simple operation, right, for single qubit gates. That's how we convert single qubit gates into the big old product that we can multiply. So now the next question is, how do we do this for multi-qubit gates? Well, come on, everyone knows the C0 gate, right? C0 it's just matrix right here. What do you mean? Easy peasy. Okay, I'm pretty sure this is matrix. It's gonna be awkward if this is actually not what it is. Oh, oopsies. Pretty sure this is what the matrix is. This is C0, right? Easy peasy. Put that in code and you're done. Like, right? Or it could be controlled anything, right? This is the controlled anything is 1 1 0, right? The identity 0 0 0 0 0 0 0 0, and then this is the matrix down here that's controlled by it. So this could be Z or anything like that. So then what, and the reason, right, is because the controlled operation is the I. That's okay, but it doesn't matter. But how do we convert this? Suppose we have 3 qubits and we're doing 0 0 0, right? And we want to do boop down to here. How do we do that? Now that's a tougher question, right? How do you do this process and in this system? And I'll tell you how. The key is to just there's just a formula for this, right? I'm not going to go over to derivation, but we know C0 is also equivalent to, assuming C0 0, 1 is equivalent to, this is why, remember, we're using the outer products. This is what the C0 gate is, right? And so we can see, if we're doing this whole matrix out, we can separate this into 2 things. Right, this is one matrix. This is the 4x4, right? Remember, because the outer product was 1 0 0 0. And so this identity goes right here, and the inner product of 1 1 means this x goes right here, right? And so that's why that is what it is. But we can also say, hey, wait a minute, if we want to do this, we can say, okay, we can go through and say, okay, well, if we have n qubits, right, we can just put its identity on the n qubits. If this is actually C0 maybe 3, 5, right? We can do, so that's 0, 1, that's 0, 1, 2, 3. Oh, oopsies, 3 was the, so now we have 3, right? And we want to do the outer product, and 4, and we have 5, right? So this is, right, it's everything's identity except for this outer product part, which is on the controlled qubit. And then we can say, okay, well, let's look at the next one. 1, 2, 3, or 0, 1, 2, 3, 4, 5. And now we can do the outer product down here, and then we can add them, and we'll get the full matrix. And so this is oh, well, I should actually, oopsies, my bad. Whoopsies, this is actually whoops, hold on. Yeah, this is my bad. I went through the whole thing without paying attention. Right, just, I was right above. That's not wrong. I just completely skipped over it, right? This is, there we go. And then this will be gate. This can be X, for example, right? So these outer products, right, are the controlled qubits. Just like up here, right? This is control 0, 0, and this is index 1, 1. And so for the target, right, the target, you can think about this as the target part, if you will, and this is the control part. I don't know if that's the best way of thinking about it, but that's one way to think about it. The target doesn't do anything to the control qubit. And so this is where we say, okay, for the algorithm for any single control qubit operation is you, hold on 1 second. Okay, so we can see this is the general algorithm, so it might make more sense even if we look at the code. So now we can see for the multi-qubit gates, or the single control, single target, for the single qubit gates. Wow, I said single a lot. First we get the control, and notice I don't do any programmatic error checking, and that means, like, okay, if you set the control and the target to be the same thing, my code will not tell you it's wrong. It'll just break. So, I rely on the user to, it's not like a real development quality simulator. So yeah. And so the control is, we saw down here, right? Defined. This is control. This is target. And so, which means, oh my God, wow, this is just not my day. This is not, this is control. I can't write. This is control, and this is target. Wow, that is that's embarrassing. And you can see, yeah, this is control, right? Right here, this is control, because this is control, and this is target, right here. Anyway, now we can get into code. So we have the two sets. Remember, so this is remember, we're adding them. We're adding these two matrices. So we can see, we can go through all the number of qubits, right? And we can say, okay, if this is the control qubit, we do the outer product of 0, 0, which was defined over here. And we do that. And if it's for the second matrix, we do the outer product of 1, 1. And if it's the target, for the first operation, remember we did the tensor product with I, or the identity matrix. So that's what we do here. And if it's the second one, which means we're doing the outer product of 1, 1, then we do the gate operation. And then if it's anything else, we just do I. And so now we have the two lists of operations that we want to do, right? And so we can just Kronecker them all together, and that's exactly what we do. We do Kronecker, and then for all the qubits, we Kronecker them together. And so this is just doing the tensor product automatically to create the full matrix, and then we add them together, and we get our final op, and we can return that. So that's basically all you have to do. And that's pretty straightforward, right? You just had to realize that you could separate. I shouldn't say realize, this is well documented in literature, is that you separate them out and then you can do this this operation. And so this is a technique. You can do multi-controlled things, you can do arbitrary, there's information out there to do all of them, but this is just an example of how to do the single control. So now let's get to some examples. I'm actually going to combine these together more. So the first thing we want to do is we want to test, let's just test our simple X circuit, right? So this is how we set up the circuit, right? We get the number of qubits. In this case, we're doing a single X test. We create our circuit, right? And in this case, it's just X on qubit 0. We run the circuit, giving it the qubits, giving it the test, and specifying number of measurements. And then we can print the output. So if I do that, let me go over. We can do Python task 3. We can see it's measured 1 for all 1,000 tests. And that's exactly what we would expect, right? Because it's, it's just an X gate. That's what it does. And it's starting in the ground state. So now we can say, hold on, let me see if I can do this. Oh, no, it puts them on top. Oh, that's a pain. So now let's test the another simple one, and this one is getting the sort of testing the operations of the multi qubits with single gate, right? So we have X on the second qubit, and we do the exact same setup. So we can go over, and because I put input statements, right, I'm just gonna hit enter. And we can see, yep, 0, 1, right, is what we'd expect every single time. And now we can go back and we can see, okay, now we're creating the Bell state. So we do the Hadamard gate on the 0 state, the X, the first qubit, right? It's weird saying first because it's index 0, but, and then we do controlled. And so this is how to format, right? You give it an op, like a gate op, without any qubit, right? It's default none. So there's no qubit specified there. And then you do control target. So if we do that, we can go back over and we can see, wow, would you look at that? 0011 measured almost equiprobable. And now we can test a little bit of a bigger system, and that's a 10 qubit GHZ state. And so the GHZ state, I'm just checking who it's named after real quick. Named after Greenberger, Horn, and Zellinger. I don't know who they are, but it's the state. It's sort of like an extended Bell state where it's just, oh, I should do this. Where GHZ is simply the extended. So if we have Bell state, right, this is the Bell state, right? Oh, this is, should rename that. This is Bell. So now GHZ is like this, except just sort of extended. So we have 0 n plus 1. I don't know if this is actually the correct notation, but the idea is there. So that's the state, right? So for a 4 qubit system, the GHZ state would be 1, 2, 1, 2, 3, 4 plus 1, 2, 3, 4 all over 1 over square root of 4 is 2. Oh, and you might be able to hear my cat yelling to get in, so wants to get into my room, so I'll deal with that second. And so that's the GHZ state. That's the GHZ state. It's a strongly well, it's an entangled state, right? Just like the Bell state. And it's pretty easy to do. Oh, I just realized that's a mistake. That shouldn't be it's a silly mistake right there. This is actually over square root of 2, right? Because there's always two states that they're equiprobable. And so it has interesting, non-classical properties. There's a lot of things you can do with it, and it's interesting. But because it's also very simple to create, which is why it's nice. So if I go over and we can see the GHZ state is simply created by a Hadamard on the first gate. So right here, see, we have the Bell state. This right here is the exact same as the Bell state. Then we just keep applying controlled X's to the next qubit. So, we start at the top, target is right below it, and then target's below that one, and then target's below that one. So you're just taking a C0 gate and moving it down sort of the qubit line. And so, you can see we're just taking, 1 was the target, now it's control, 2 is the target, now it's control, and you're just moving it down. And so we can see, if I go to the code, open that up, this one, you'll notice, I'll tell you when I hit enter, and you'll see how long it takes. Enter. And so you can see that was noticeable. I mean, it wasn't long, but it was noticeable in its time. And that's because 10 qubits is starting to get up there in the matrix multiplications that it has to do. And so we can see equiprobable 1, 1, 1, 0, 0, 0. So next up is something that you might be familiar with, but I have not talked about it yet in the intro series, and that is Grover's algorithm. And so this is a 2-qubit example. It's not very exciting, but so for Grover's algorithm, we have the initial superposition. We apply the oracle, which in this case is for the state 1, 1, because it's controlled Z, which means, remember, the oracle flips the desired state to the negative. Controlled Z has the effect of flipping the all 1 state to negative. Then we apply the diffusion operator, which is the Hadamard on each of them, and the Z gate on each of them, then control Z, then Hadamard. This doesn't, I'm not going to go over this either. You're aware of Grover's algorithm or you're not. I haven't, talked about it yet. It will be, in the future discussed, but that's not for now. So this is just showing that you can do it. And so if we if I go over to the code and I hit enter, we can see it measured, in this case, 1, 1 every single time. And so then the last part is pretty exciting, which is, more research focused, right? If you're doing research, you might do this. This is a VQE completely from scratch, right? That's pretty fun. I don't know, that seems exciting. So we have our Hamiltonian as defined. This is the identity term or the constant added to it. This is the X term, the Y term, and the Z term. We have a single parameter. So we're using this time the RY gate down here with the parameter. And we're applying it to the only qubit that exists. And so the X circuit is the parameter gate, and then the readout operator, right? We have to change the direction for the Hamiltonian, right? And so that's why the Z doesn't have this term, is because this is adjusting the Hamiltonian so we can read out things. We measure it 1,000 times, we create the qubits, and then we run each of these circuits. And to get the expectation value, we take the difference, right? So remember that 0 and 1 get mapped to eigenvalues of 1 and -1, 1, right? we're mapping them because 0 and 1 are the states that we associate them with, but they're not the eigenvalues of the measurement. And so we can see that, if we measure every single thing in here versus every single thing in here, right, this will be completely in the 1 eigenvalue. This will be completely in the -1 eigenvalue. And so we have to estimate, approximate what it is. So we subtract them and divide by the measurements, and then we can return the estimated Hamiltonian. And so we can plot what this looks like now. So I will hit enter, and let me show you the plot. I have to actually add it as a screen now. Yeah, I hit enter. It doesn't show anything. There we go. So that's what it looks like, right? And we can see that the VQE minimum down here. And so, yeah, that's pretty much it for the demos. So, yeah, I encourage you to try this out for yourself. And if you want to do further implementations and make pull requests or whatever, you can do that. But yeah, so this is, you can see it's pretty straightforward actually to make the basic circuit simulator from scratch. And so, yep, that's all for today. Oh, wow, that was long. That's the part 4 of the intro. That's the QOSF, what not to do, quantum circuit simulator from scratch.